Welcome back, guys, to Urban Odyssey. This is the first episode of 2026. I hope everybody had a great new year. This is going to be section 5 of our 6G and beyond white paper walkthrough. All this and more after the intro.
All these transactions are personally authorized by you. The board of directors will crucify you.
I suggest you just relax, because everything's gonna be fine.
There's something strange inside that man's head.
Alrighty, ladies and gentlemen, I hope everybody is doing well. I hope everybody had a good holiday. Just got a chance to relax and kick your feet up and just kind of forget the troubles of the world for a day. But 2026 is definitely going to be a roller coaster of a year. There's no doubt about that. And hopefully, some of the things that we see this year you will better understand, if nothing else, because of the information that we're going through in this series. Because this is going to be, as I see it now, kind of a defining characteristic of it, at least the next 10 years, probably. And the next 10 years are going to be probably crazier than anything we've ever seen before in recorded human history with technology and artificial intelligence, etc. With that being said, this fifth section of the white paper is entitled Pervasive Artificial Intelligence. And it's not too long of a section. It's a little bit better than the past two that we've done. And with that, guys, let's just go ahead and get right into it. Section 5, Pervasive Artificial Intelligence. In the past few years, the field of artificial intelligence, AI, has witnessed immense growth, leading to its application in a wide variety of fields across both academia and industry. In the realm of communications and signal processing, AI can be readily applied to cognitive radios and remote sensing, computer vision, and network management, more specifically in the domain of wireless communications. AI and its associated algorithms are also gradually proving their utility in various emerging technologies such as massive MIMO, which is multiple input, multiple output communications, which requires efficient channel estimation and symbol detection. Such tasks often do not yield low complexity optimal solutions in complex channels, and thus parallel processing inherent in machine learning can be favorably leveraged to enhance computational capacity. Admittedly, even though current wireless communication networks follow a layered structure in which each layer primarily serves several functions, applications of AI relevant algorithms, let me zoom in, are currently bridging the gap across layers in a way that can globally optimize the performance in the entire wireless network. However, in order to provide a marked trail to navigate through a plethora of pervasive AI applications, this section is organized based on the existing layers. It is worth noting that AI is a broad concept under which reside several branches covering interleaved research topics such as robotics, natural language processing, machine learning, computer vision, among others. In this section, we focus specifically on the machine learning algorithms and their applications in wireless communications under the AI umbrella. These two terms are thus used interchangeably. In this section, as shown in Figure 5, here's Figure 5. Artificial intelligence can be applied to each layer of the wireless network. At the network layer, machine learning algorithms can be used for traffic clustering to further adapt the network resources to various scenarios. At the physical layer and MAC layers, deep learning can optimize resource allocation strategies for power distribution and modulation and coding schemes, among others. Furthermore, machine learning algorithms can also assist with channel estimation and multi-user detection. And so basically, in a very simple way of putting this, the idea is to implement AI and machine learning at all of the layers and allow it to solve different problems on different layers. That's a very simple way of putting it. Okay. The first subsection A, AI in the physical layer. Traditionally, physical layer modeling has been model-oriented, a practice in which mathematical models following a certain framework are proposed and optimized under constraints to satisfy a series of predetermined performance requirements. For example, in order to conduct channel estimation, a channel model is assumed along with other parametric configurations. These model-based solutions usually perform well if the derivation of mathematical models is relatively straightforward, or there exists a closed-form solution. The models can then be validated by field measurements or numerical simulations. However, in real-world scenarios, the applicability of such model-based solutions falls short in complicated environments due to factors such as non-linearity inside systems and uncontrollable interference, among others. On the other hand, another approach, which is based on statistics or data sets, builds the model through learning from the data. This method is particularly useful when theoretical analysis is intractable or when a closed-form solution is difficult to obtain. For example, in diffusion-based channels commonly found in molecular communication, the channel characteristics depend largely on the environment, making them challenging to model theoretically. In such cases, some data is used for training, which can help establish a model, while other data is used for testing in order to validate the model. To date, artificial intelligence has demonstrated its usefulness in various physical layer techniques. For example, in channel estimation and symbol detection, deep learning approaches reported in citations 78 and 79 have shown that the proposed deep learning-based symbol detection algorithms can provide robust and accurate results with reduced complexity. Furthermore, a deep learning method based on the deep neural network architecture also demonstrates an improved channel estimation accuracy under the effects of non-linearities of power amplifiers, I-Q imbalance, and quantization errors induced by hardware impairments. An autoencoder-based communication system is proposed to reconstruct the transmitted signals from channel impairment based on trained deep neural networks in an end-to-end manner. Furthermore, self-supervised learning, and I made a little note here so that we can learn what that is. I'll read it to you. Self-supervised learning, and I've got some like little clips on what that is because I had to learn what that was, and I will put the links in the post, in the description, and give you links to like the YouTube videos that explain it. Self-supervised learning, SSL, is a machine learning method where models learn from vast amounts of unlabeled data by creating their own supervisory signals or pseudo labels from the data's inherent structure, allowing them to discover patterns and features without human annotation, making it a powerful bridge between supervised and unsupervised learning, especially useful for foundational models in NLP and vision. It works by defining pre-text tasks like predicting missing image patches or text that force the model to understand underlying data relationships, then transferring this knowledge to actual downstream tasks like image classification or summarization by fine-tuning or linear evaluation. And I'll put that link in the description. And let me go ahead and show you the images that I had saved. Okay, here's the first image that I was able to find on self-supervised learning. Here's the second image on self-supervised learning. And let me fit that to the screen. That is the final image. Okay, so that's self-supervised learning. If you want to know more about that, there will be links and videos that you can check out. Self-supervised learning is becoming a trend for user localization, since it has been demonstrated that relevant methods can significantly reduce the size of labeled dataset for efficient processing. So user localization, if you remember, I think I mentioned that last video. Localization just means adapting it for kind of specific use cases, or localizing it to a specific user, city, state, etc. Subsection B, AI and wireless networks. In other essential layers of a wireless network, the existence of rich datasets lends itself to the applicability of machine learning-based solutions. In routing protocol design for wireless sensor networks, researchers have successfully utilized reinforcement learning methods to achieve a more energy-efficient routing scheme for underwater sensor networks. In the vehicular industry, autonomous driving has already been studied and became a reality in some cities in Arizona in the United States. With respect to vehicular communication networks, due to the constant movement of vehicles, a predictive model based on real-time data has superiority over traditional theoretical models in terms of accuracy. Artificial intelligence and its plethora of algorithms can be applied in varied ways in such networks. Autoencoders for predicting traffic flow, K-means clustering for traffic congestion control, and Q-learning for intelligent resource management. I highlighted that just because I thought it was interesting that Q-learning popped up, or just Q, because that's a, something that pops up. Interesting to notice that Q is associated with the 17 because it's the 17th letter of the alphabet, and the number 17 is significant for various reasons. Q-learning for intelligent resource management, among others. In the Internet of Space Things, with our envisioned multi-band communication capabilities and both inter-satellite and ground-to-satellite links, we have proposed a deep neural network-based resource allocation strategy to enable a flexible scheme for CubeSats to stay connected without human intervention from the ground. Got the note here. Let's see. A CubeSat refers to satellites that have a cubic structure, 6 square faces of equal size whose sides measure 10 by 10 centimeters, which is 3.94 by 3.94 inches, and weigh about 1 kilogram or 2.2 pounds. They are either launched as single units or as part of a group up to 24 units of such satellites. The exterior of these satellites is made largely of aluminum, and the interior of the satellite's houses a power source of some kind, like battery or solar panels, B, an antenna for sending and receiving information, C, a computer which has regulatory oversight of the satellite's components, D, components such as sensors, instruments, and cameras which are constructed specifically to serve whatever the mission of the satellite might be. It says as of 2024, there are more than 510 of these CubeSats in orbit. And I'm not going to read the whole thing, but I will put that in the Substack post. To CubeSats to stay connected without human intervention from the ground. Apart from advancements in algorithm development, a potential issue dwells on the location of data storage and processing, which has largely happened in central data centers in the cloud. For devices distributed in a wide geographic range, this undoubtedly adds significant delays in performing tasks which would require real-time operation. Moreover, a centralized computing manner is not desired from perspectives of data security and constraint and processing capacity. In order to relieve such challenges, Edge AI pushes local devices to fulfill operation and management tasks. Admittedly, this could lead to possible overburden in local devices, since they are not equipped with as powerful processing units as the cloud processing center. However, research efforts in this direction are dedicated to 1. Acceleration in boosting the hardware's processing capability, and 2. Leveraging the coordination between local and central processing units to optimization task distribution. Subsection C. AI and network management and orchestration. AI, or more specifically machine learning, has an integral role to play in the management of networks. In fact, Clark et al. Introduced the concept of the knowledge plane back in 2003, describing it as a pervasive machine learning based system within the network that is geared towards providing services and advice to other elements of the network. More recently, with software defined networking, SDN, network function virtualization, or NFV, becoming mainstream, large-scale data acquisition has become easier than ever before, making a strong case for machine learning-based management and orchestration primitives within 6G, ultimately leading to full network automation as discussed in the next section. In particular, the domain of network management presents a wide variety of problems that can be broadly categorized into supervised learning. Supervised learning is typically applied to problems relating to traffic prediction and classification, as well as slice resource prediction, while the former primarily involves preemptively determining the network traffic load, as well as determining the applications, protocols, and QoS classes the traffic belong to for fine-grained traffic. Engineering. The latter involves predicting the resource requirements associated with different network slices based on the anticipated traffic load. Reinforcement learning. Reinforcement learning typically finds use in problems associated with resource management. For example, the popular virtual network embedding problem, wherein the network orchestrator performs optimal placement of virtual network functions onto the underlying physical substrate. It is highly amenable to reinforcement learning. Other applications include elastic scaling of network infrastructure, failure prevention, and configuration rollback. Unsupervised learning. While both supervised learning and reinforcement learning have shown significant promise in the network management domain, we note that there exist certain use cases, such as those relating to optimizing the end user's quality of experience, QoE, in network security, where 1. Labeled data for training is simply not present, and 2. The real-time nature of the application makes it impractical to wait for feedback in such cases. Unsupervised learning can prove to be an indispensable tool. For example, intrusion detection systems based on autoencoders have been shown to outperform supervised learning-based systems. Open problems for pervasive AI, subsection D. During the early years of 5G standardization, researchers have discussed potentials of AI in achieving high time and spectrum efficiency once incorporated in 5G. Specifically, AI algorithms can help facilitate the following tasks, which would yield low efficiency with conventional solutions: identify network anomalies, allocate network resources, perform network management, among others. However, so far these solutions have not been officially adopted in 5G standards worldwide. In June 2020, the ITU has initiated an AI/ML in 5G challenge to motivate researchers to identify and solve real-world problems using artificial intelligence and machine learning solutions in relevant 5G directions. I don't know what that is, and it does give you a little citation there. As such, it is envisioned that such efforts would be factored in later 5G developments, but will be materialized in a more concrete and pervasive manner. There's that word again, pervasive. It just keeps popping up, doesn't it? Pervasive manner in 6G. While pervasive artificial intelligence in wireless communication networks will undoubtedly bring a paradigm shift towards data-oriented approaches, there are still open problems to be resolved. First, thus far, no agreement has ever been reached on which algorithms work the best to solve a generalized problem in wireless networks, such as modulation encoding scheme design, channel estimation, and resource allocation, among others. Almost all published works claim significant accuracy or reduced complexity with either analytical theories or practical data sets. Additionally, we note the absence of an effective method to draw a fair comparison among all proposed solutions due to variations in selected data sets, assumptions, evaluation criteria, and so on. However, when it comes to realistic deployments, a careful gleaning process should be performed in order to identify algorithms without loss of general applicability. Second, the limited availability of quality data sets is detrimental to the testing and validation of proposed classification or regression algorithms. And with that last part there, what I'm immediately thinking, 2026, this was 2020, and so with all of the AI content on the internet now, they're talking about how it is going to not be good when that, AI is training on its own AI generated results. And so I think that quality data set issue at the end is probably made much worse now, right there. I think that's a big problem with all the AI generated content. Let's see what this little citation said. Yeah, so that citation at the end right there is something, the problems that they basically brought people in and gave them a prize if they were able to solve. I'm not going to go through these. I'm just going to leave a link to it in the description because there's all kinds of stuff here. And this was from July 2020. So these problems have probably long since been solved. Remember, 2020 would have been before all of the chat GPT and all that stuff came out. So was really arguably a little bit of a different world than we're used to today back then. Okay, guys, that is going to finish up the 5th section, and I will see you for section 6. Take care, everybody.